My name is Namsong Lee, and today I will be presenting my term project titled Performance Analysis of SSD DRAM Cache Sizing under Virus Workload Patterns. Let's start with the motivation. As you know, modern SSDs utilize DRAM as a buffer to bridge the speed gap between the high-speed host and the slower NAND flash. We commonly assume that the bigger, the better. When it comes to memory, but does this rule always apply to enterprise environments? My object was to challenge this assumption and find the optimal sweet spot by analyzing the I/O latency across three different DRAM configurations: 128 megabytes, 512 megabytes, and 1 gigabyte. Moving on the methodology, I conducted the experiments using the MQSIM simulator in the Ubuntu environment. For the workload, I utilized Microsoft Production Server traces, which represent real-world financial transaction patterns. One major challenge was that the raw trace file lacked the device ID required by the simulator. To solve this, I personally developed a custom script to process and fix the trace file before running the simulators. Here is the experimental setup. I configured three distinct models, ranging from low-end to high-end. Crucially, to ensure a fair comparison, I maintained a fixed 64:1 ratio between the data cache and the mapping table for all configurations. Now, let's look at the results. Starting with the read-intensive workload, the result was quite surprising. The smallest 128 megabytes configuration achieved the fast response time of 1.32 seconds. In contrast, the 1 gigabyte model, which has 8 times more memory, was actually slower at 1.41 seconds, showing a performance drop about 7%. We observed similar trend in write-intensive workload. Again, the 128 megabytes model performed best at 1.02 seconds. As you can see, increasing the cache size resulted in diminishing returns or even stagnation. This clearly proves that a large cache does not always guarantee better performance. So we did get these contradictory results. The key reason lies in the cache management overhead. A large DRAM implies a much larger mapping table to traverse. However, the Microsoft workload used in experiment is highly random. Because of this randomness, the time cost of searching through a massive 1 gigabyte table overweighted the benefits of having larger buffer. To analyze this further, the workload likely had a working set that was too scattered, causing frequent thrashing even with 1 gigabyte of memory. Therefore, a linear cache like 128 megabytes model was much quicker to manage and search. The key insight is here. More hardware is not always the answer for random workload. In conclusion, I successfully automated the MQSIM simulation with custom trace fixes. Based on the experimental data, I concluded that investing in 1 gigabyte plus DRAM for this specific workload is not cost-effective. Therefore, I recommend the 128 megabyte configuration as the optimal choice for this environment. That concludes my presentation. Thank you for listening.